this talk is Materials-Driven Approach to Discovering and Understanding the Materials of the Future. And I want to start off just by saying that this is going to be sort of a big picture overview of a very broad topic. So I'm not going to go into a lot of detail. It's meant to be more friendly, especially to folks who aren't coming from the world of materials physics. And so if you were hoping to see slide after slide of dense graphs and data, this isn't the talk for you. So this is meant to be more of a broad overview. And to motivate this, let me start off by asking kind of a simple question. What do we make our technology from? And that's a simple question, but it actually has a lot of complicated answers. And one sort of oversimplified answer might be, well, we make them out of materials. And if we make them out of materials, which materials do we choose? Well, that really depends on, of course, the technological application we're working on. So basically, given a particular application, we identify a set of properties that our material has to satisfy, and then we pick the one that satisfies those the best, and often has the best properties that are available to us. And of course, even that's a little oversimplified because, you know, in addition to having the right properties, that material also has to be relatively cheap and abundant and easy to process and generally non-toxic. So there are a lot of requirements that go into this. But, you know, if you kind of buy this premise that we pick the materials with the best properties, what that tells us is that better materials or those with enhanced properties might be able to develop better or more efficient technology. And so this is one way that materials research can help drive technological advancement and innovation. And so I have here a very, very short list. There are many more, of course, but of technologies of the future that people are working on now. Things like quantum computing, thermoelectric devices to power, let's say, unpersoned spacecraft, magnetic refrigeration to replace our really energy inefficient vapor compression technology we use in most cooling devices now, superconducting circuits, but that we don't need to cool down with liquid cryogens and can operate at room temperature. Strong permanent magnets, but that don't contain rare earth elements that are kind of a strategic element that are a little bit hard to find, and many, many others. So what sorts of materials might enable some of these technologies? Well, broadly speaking, a lot of them we're going to call correlated electron materials. And in this talk, I've got, you know, this relatively simple outline and this set of objectives. I want to start off by sort of giving, again, kind of a big picture, broad overview of what we mean by correlated electron materials and the properties or phenomena they exhibit. Then I want to talk a little bit about how we make discoveries, you know, how we discover new correlated electron materials or understand the properties they exhibit. So that's the second part, and that's kind of the research approach. And then there'll be a little bit of time at the end where I'll be able to showcase a little bit of some of the student research done here in my lab at Central that makes use of this research approach. So let's start off with our introduction to correlated electron materials and phenomena. So if this was a seminar in which we were, you know, sitting in a room together in person, you know, I might hand each of you a box with these are pictures of samples that were synthesized in my laboratory. And I might ask you, what are the properties of these materials? And in looking at them, you might, you know, kind of look at them and say, well, I don't know, they're kind of small, black, brittle discs, you know, they kind of chip off if I, you know, kind of poke at them. And okay, those are characteristics of those samples, but by properties or phenomena, what we're asking is questions more like how well or poorly do they conduct electricity, or how well or poorly do they conduct heat? If the samples contain magnetic moments, do we observe magnetic order or disorder? And if we have magnetic order, what are the properties or characteristics of that order? If I apply a magnetic field to them, will the samples change temperature? That can happen. That's something called a magnetocaloric effect. If I apply a temperature gradient, basically heat up one side of the sample and kind of keep the other cold, will they generate a thermoelectric voltage? That's a thermoelectric effect. are the properties that I measure at a specific temperature, like room temperature, the same as the properties I see at low temperature? Basically, how do these properties change as a function of temperature? And just in general, how easily am I able to modify these properties by doing things like chemical substitution? So that's replacing one element with another element. Applying pressure, that's basically squeezing the materials, and that can be done either hydrostatically or uniaxially. Applying stress, applying magnetic or electric fields, temperature gradient, shining light or other electromagnetic waves on them. So basically I want to know, how do those properties change when I modify the conditions those samples find themselves in? Now, when we're talking about correlated electron phenomena, I'm going to put a very partial list of some correlated electron phenomena here, and let's see if you notice a common feature with them. So we've got things like colossal Seebeck or thermoelectric effect, high temperature superconductivity, colossal magnetoresistance, colossal magnetocaloric effect, heavy fermion physics. You get a sense from reading those off that, a lot of these are properties that, maybe more boring materials could possess. But when we're talking about correlated electron phenomena, we have these sort of superlative adjectives that go on there, things like colossal or high temperature or heavy, and it's telling you something about the fact that these phenomena tend to be enhanced properties relative to those exhibited by or weakly correlated materials. And there's some other common features we find among correlated electron phenomena, like on that list there. One thing that is often true is we tend to lack a comprehensive understanding of the underlying mechanisms. We don't really know everything we need to know to develop a theory that explains everything about how that property works. And sometimes that means, maybe even decades after we discovered the property, we're still not completely sure how it works. Maybe there's a lot of theories out there, but not consensus around which is the correct. And because, as I'm going to sort of justify in a few slides, it's so complicated to develop theories or do calculations with materials, these phenomena tend to be discovered experimentally. So they're not predicted theoretically first. They're often discovered in the lab, and as I'll talk about later, often completely by accident. And then, as mentioned, these tend to be potentially revolutionary, often record-breaking properties. So what sorts of materials are correlated electron materials and exhibit these types of phenomena? Well, we're not usually talking about elements or binary compounds or alloys. Usually we're talking about more complicated materials that include 3 or more elements, arranged in more complicated crystal structures than you tend to find among the elements. So more complicated materials. And in the next slide, I'm going to talk a little bit about the ingredients that sort of go into making a solid material. But here we can talk about how they're composed of a lattice, basically a periodic arrangement of ions or atoms. They contain all kinds of electrons and protons, so there's charge. The electrons also have spin and orbital angular momentum. So each of these ingredients we can also call a degree of freedom. And in correlated electron material, these tend to be highly coupled through all kinds of interactions that are happening within the material. And these interactions, each interaction tends to lead to a particular type of ordered state or behavior. And if you've got many different interactions that are on similar energy scales, there are many different possible states your material could find itself in. And so, these states sometimes compete with one another, sometimes they cooperate or can even coexist. But what this leads to is very rich phase diagrams. So for example, just picking at random a particular correlated electron system. So this is a phase diagram. So we've got temperature on the y-axis. And the system is calcium-2, ruthenium, oxygen-4, where you're systematically replacing some of that calcium with strontium as you go across the x-axis here. And if you count it up, you've got about 8 different possible states that you can access simply by tuning that ratio of strontium to calcium. And again, that comes back to the fact that there's a lot of different interactions, a lot of possible states that you can tune this material to simply by adjusting its conditions. And so correlated electron materials research really offers an appealing blend of fundamental scientific interests, which is kind of what attracts me to it, but also the potential to revolutionize technology. And that's why the public and funding agencies, really care about it. So, if we have the possibility of accessing enhanced properties in these correlated electron materials, we'd really like to be able to maybe predict which materials are going to exhibit the enhanced properties we need for whatever our technological application is. So one might ask, okay, how easy is it for us to do that? And unfortunately, the answer is not very easy. And so I'm going to talk a little bit about why that is, simply by talking about, solids sort of in general. So, if I have a really simple model of a metal right here, I have numerous ingredients that are found in there. So I have this lattice of these positively charged ions. So this is a periodic arrangement of ions that forms a lattice. These little blue circles, those would represent the electrons in your metal, and those are free to wander a little bit throughout the metal. And obviously electrons have charge, so we've got charge in there. Electrons can have spin and orbital angular momentum. So there's all kinds of these ingredients that are found. And when you have orbital and spin angular momentum, sometimes you can add those together to get a non-zero total angular momentum. And anytime you have a non-zero total angular momentum, you've got a magnetic moment. And a magnetic moment, that's kind of shown over here in this picture as these little arrows. You can kind of think about those as microscopic little bar magnets that maybe exist on the ion forming the lattice, for example. And so now with that, you have this additional degree of freedom because they can interact with one another. And you can see here, they're all pointing kind of in random directions. So this would be an example of magnetic disorder. But you can see that there's all kinds of ingredients here. And then, these pictures on the left and right-hand side are static, right? Nothing is moving. But of course, at elevated temperatures, there's a lot of energy in the material. So these are dynamic pictures. The electrons are able to move around. These arrows would be pointing in random directions, basically fluctuating around. And you can see here, even the lattice in this image in the middle here, those ions are moving around. Basically, they're free to vibrate a little bit around or oscillate around their equilibrium positions. So, in addition to having all these ingredients and all these interactions, it's also extremely dynamic. So basically, we have all kinds of complicated, often quantum interactions that occur on various length, energy, and time scales. And because these interactions often promote one type or another of a state or behavior, we've got many different more or less degenerate states that the material could choose between. And that's one of the nice things about them is often we can tune between these states by doing things like replacing one element with another, chemical substitution, squeezing it, applying pressure, or things like applying a magnetic field. So there's a lot going on inside materials. And so, that's really materials in general. What do we mean specifically about electron correlations? Well, it's maybe easier to start by talking about, what we would mean by saying electrons were not correlated. And so, one of the nicest ways of doing this is to think about sort of the historical development of theories of materials. And the early theories of materials focused primarily on metals. Metals obviously were important for engineering purposes and also are relatively simple for them to focus on. And so the first model of a metal that was successful was due to Paul Drude. And Paul Drude was aware that metals contained, a lattice that was generally positively charged ions and electrons which had charge. But in working through his model, he quickly realized that he would not be able to include the electron-electron repulsion, right? Two electrons are going to repel one another, and an electron with a positively charged ion, there's going to be an attractive interaction. But he was quickly unable to do calculations that really accounted for these interactions. So rather, he made some rather drastic assumptions. His model said basically, okay, I've got a lattice, but I'm going to say that the ions are not charged. And I'm going to also say that the electrons are not charged. That basically the electrons are bouncing around almost like pinballs in a pinball machine. And scattering, of course, occurs, but it's just sort of ballistic scattering off of these immobile ions. And so this choice was forcing him to assume electrons were independent, and by independent we mean no interactions with one another, and free. And by free we mean they weren't interacting with any potential energy landscape from the lattice of ions. And so in such a picture, he was able to use just the theory of classical gases at the time to try and come up with some properties that metals should obey. And the theory was quite successful. He was able to explain a lot of the observations that people made about metals at the time. But it was a classical theory that has these drastic assumptions of free and independent electrons. In 1927, a prominent theorist named Arnold Sommerfeld was able to insert quantum mechanics into that model. So basically, you know, quantum mechanics was coming around at that time. He recognized that metals better obey quantum mechanics. And so he made sure that, you know, he basically considered an electron gas as well, but made sure it was solutions of the Schrodinger equation, and made sure that electrons obeyed the Pauli exclusion principle, so that no two electrons can occupy the same state. However, you know, that was a success to sort of insert quantum mechanics into the theory. He was unable to put that charge back on the electron and put the charge on the ions in the lattice. It was still far too complicated for him to do that. So this is still assuming free and independent electrons. And the following year, Felix Bloch was able to relax one of those restrictions. So Felix Bloch recognized that, okay, I'm going to put the positive charge back on the ions in the lattice, and that's going to produce a periodic potential energy landscape that the electrons are interacting with. And so that now means the electrons are no longer free electrons, but I still can't deal with electrons and their interactions with one another. So I still have to assume they are independent from one another. And in using that periodic potential energy and inserting that into the Schrodinger equation and coming up with the wave function solutions, he found solutions which are, you know, basically plane wave solutions or traveling waves. So the electrons act like kind of we might expect them, you know, objects that are moving through the material, and they're modulated by some function that also carries with it the periodicity of the lattice itself. And so in Bloch's solution, okay, we've got some, we've relaxed one of the assumptions, and we've also been able to build up band structure. So that was a big improvement. But in all of these models, we had to completely neglect electron-electron type interactions, and that's really what we're meaning by these correlations. So how do we move beyond Bloch's solution? Well, in general, whenever we do quantum mechanics, it always boils down to solving the Schrodinger equation. So the Schrodinger equation is right here. It's a partial differential equation. And it always looks like this. And the thing that changes whenever we consider a particular situation or system is this operator right here we call the Hamiltonian. And the Hamiltonian basically represents the total energy of the system. All of the kinetic energy, that's the energy associated with motion, and all of the potential energy, that's the energy that could be used to provide motion. And in Bloch's Hamiltonian, basically he was accounting for the kinetic energy of the electrons and this periodic potential energy from the lattice, and that was it. So in more realistic systems, okay, at minimum we have to include the kinetic energy of the electrons and the potential energy from the lattice, but we have to include other interactions as well, because, you know, real systems have so many other interactions. You know, those could be interactions like the Coulomb repulsion between electrons, right? Like charges repel one another. You know, spin-orbit coupling, crystal electric field effects, magnetic exchange interactions, classical dipole-dipole interactions. If we apply a magnetic field, Zeeman splitting, electron-phonon coupling, and the list could go on and on and on. There are so many different interactions we could consider, and that's where this gets complicated. Now, in simple materials, we might get lucky, and so the easy situation would be, so there'd be an energy associated maybe with each one of these interactions. And if the hierarchy of energy scales is such that they're all relatively separated from one another, it's a lot easier for us to say, okay, well, this one is the most important and I can neglect these other ones down here. And so now, you know, when I tack on my other terms to the Hamiltonian, I've got fewer terms I'm working with, and it's easier to see, you know, which one is most important, which is second most important, so on and so forth, because when you do quantum calculations, you're often doing things like perturbation theories and whatnot. And so you kind of have to know that to be able to follow through on that calculation. Unfortunately, or in actuality, fortunately, because it's a nice outcome, for correlated electron materials, we tend to have a whole bunch of different interactions with relatively similar energy, which means that, you know, if I say this one is important, I really have to say all of them are important, which means I have to account for a lot of interactions at the same time. It's also a little harder to know, you know, which one is most important, second most important, third most important, because sometimes they're pretty close in energy. And the issue is that when theorists work on these calculations, you know, they have to make some assumptions about which interactions they're going to account for and what that hierarchy of energy scales looks like. And what that means is that, you know, the outcome, what theorists predict will happen for a material, is largely dependent upon those choices. And not every theorist makes the same assumptions or approximations or choices, which means for a particular material, in doing calculations, you know, 10 different theorists may end up with 10 different answers about what you might expect. It's a hard thing. It's a hard thing to calculate. Now, one of the things that I'm not going to go into a lot of detail here, but you know, those early models I was talking about, like the Sommerfeld model, a quantum electron gas, one of the results that comes from it is if you plot out basically the different quantum space states in K space, and if you have a bucket of electrons and you fill each of those states, the lowest energy state first with an electron, and then the second lowest, and then the third lowest, what you'll end up with at the end at zero temperature will be, you know, some sort of a shape which represents well, a lot of the details of that quantum gas. And for the Sommerfeld model, this is what we call the Fermi surface. So basically, this would represent all of the states that are occupied by electrons. And again, that was a very simple model, free electron, independent electron. However, if I take that and I compare it with some simple materials, like for example, copper. So here's a chunk of copper, and here's the experimentally measured Fermi surface for copper. It's pretty much a sphere. It's got a little bit of decoration near where the Fermi surface is sort of contacting the Brillouin zone, but it's pretty close to a sphere. And what that's telling us is that, well, copper is a relatively uncorrelated metal. Obviously, there are electron-electron interactions, but they're not so important. And you know, what do we know about copper? Well, I mean, it's an important material because it has a low resistance. We use it in our wires. But, you know, from another standpoint, it's really boring. It's non-magnetic. If you cool it down, it's not a superconductor. There aren't any interesting electron-driven phase transitions in copper. So this uncorrelated material is not that interesting. And we can contrast that with, here's some Fermi surfaces for some correlated electron materials. So these three right here are for cerium, cobalt, indium 5. This one here for plutonium, cobalt, indium 5. And what you can see is these are definitely not a sphere. We've got all kinds of crazy Fermi sheets that are built in there, all kinds of Fermi surface nesting, much more complicated. And what do we know about the properties of these materials? Well, they're heavy fermion materials. They have a high temperature superconductivity. They have an exotic high magnetic field phase called the Q phase, exotic non-Fermi liquid behavior near quantum critical points. All kinds of interesting things happen. Okay, and so, you know, these correlated electron phenomena arise from electron-electron interactions that are, you know, obviously being revealed in the complexity of the Fermi surfaces here. Okay, so if correlated electron materials and the behavior they exhibit are so complicated, you know, we might ask, okay, well, how do we discover these materials in the first place? And once we know about them, how do we understand them? Well, that's the next part of our talk. So we're going to talk about the materials-driven approach to understanding these things. So it's useful to kind of think about, you know, what most people's conception of how a physics discovery is made goes. So most people kind of have this idea that, you know, a theorist comes up with a kind of a theoretical idea or has a model, walks up to a chalkboard, does a bunch of calculations, you know, maybe develops a testable hypothesis. And then from that, maybe that physicist or maybe that physicist has a colleague that they ask, goes into a laboratory, conducts an experiment to test the hypothesis, and then, you know, maybe we get confirmation. So that's most people's perception of how discoveries are made in physics. And in the case of correlated electron research, following this sort of gold standard scientific method approach isn't so easy. And the problem is we usually get bogged down on step one. So instead of, you know, working with theoretical models, we tend to collect observations from the literature and develop empirical rules of thumb. You know, we notice that, you know, if we're interested in a particular type of property like superconductivity, that, you know, certain attributes of materials seem to keep cropping up among the superconductors we know about. And so we develop sort of these empirical rules of thumb that help guide where we're going to search next. From those, we get our hypothesis and follow through on the rest of the procedure. So the goal here, of course, is given a particular phenomenon. So this could be superconductivity, for example, or could be any of the other correlated electron phenomena. We would love to have a comprehensive theory that describes and all of the theory, all of the underlying physics that governs the process. And by comprehensive theory, we're looking for something that's capable of predicting which materials will exhibit that particular phenomenon. So ideally, we'd love to have something, a theory where we could just plug in for material X, crystal structure, point symmetries, lattice parameter values, electron density and configurations, crystal electric field effects, Fermi energy, and other attributes of the material, and out would pop whether or not material X exhibits that desired property in the required temperature range. So that would, of course, be the goal for a lot of these properties and these phenomena. So how might we achieve that goal? Well, we're going to go into how that might work, and I'm going to use superconductivity as an example for it. So before I go any further, I wanted to talk a little bit about superconductivity so we're all on the same page and know what I mean. So superconductivity is a property that's found actually in a lot of materials that tend to be metals at high temperature. And basically, if you take that metal and cool it down to low temperature, if you measure the resistance, so this is the electrical resistance on the y-axis and the temperature on the x-axis, what you'd find is that the resistance gets smaller and smaller and smaller as a function of decreasing temperature. So it's getting more and more conductive, basically, as you're cooling it down. That's a standard metallic response. And if your material becomes a superconductor, there'll be a particular temperature that will depend on what material you're looking at, where the resistance will drop to zero. And stay zero electrical resistance, generally all the way down as low as you can measure. Obviously, that has many different possible technological applications. If you can send current through a material without any through a wire without any dissipation. Of course, one of the problems is the temperature where this happens tends to be pretty low, which means you tend to have to cool it with expensive liquid cryogens. So the dream, of course, would be to find a material that is superconducting at room temperature. And when we look at this, if you think about what's going on in the normal state, it's kind of like this crowded picture of a sidewalk here that, to be honest, kind of gives me anxiety now that we live in a pandemic looking at that, but I suppose we'll return to something like that at some point. And so, all those people are walking and, they're going to get to where they want to go, but it's not going to be necessarily such a smooth walk. There's probably going to be a little jostling or maybe some stutter steps. And those are all, you can think about them as kind of collision type events. And that's what we mean by resistance. And you can contrast that with what happens in the superconducting state, where you have a coherent quantum many-body state, which is more like this marching band walking down the street. They're going to be able to march without any of that jostling or stutter steps. They're going to be able to move coherently through the street. And so that's kind of one way to visualize superconductivity. Superconductivity was discovered in 1911 by Heike Kamerlingh-Onnes, completely by accident, and I'm going to talk a little bit more about that in a second. But before we do, let me return to kind of the next subject, which was, how do we make discoveries in correlated electron materials research? And this comes back to this idea of the materials-driven approach. And the origin of that materials-driven approach is usually said to have occurred just after World War II. So again, 1911, superconductivity is discovered. It's exciting. Theorists work very hard on trying to explain and understand superconductivity for the next 35 years without much luck. They're just banging their heads against the wall. A lot of theorists, a lot of the very prominent theorists of the day are working on it and just not making much headway. And just after World War II, there was a young assistant professor at the University of Chicago named Bernd Matthias, this gentleman here. And Bernd Matthias was a materials science person. He was working primarily on ferroelectric materials back at that time. And another of his colleagues at the University of Chicago was Enrico Fermi, who probably everybody is familiar with. And Fermi, I don't know if he was working on superconductivity, but he was certainly aware of all of his colleagues, trying to develop theories to explain superconductivity, came up with an idea. Basically, he recognized that we're not really going to make much headway until we have more information. We need to discover more superconductors. We need to do more measurements on them. We need to see how they work and develop kind of a global picture. And maybe in developing it, we'll notice some things that will clue theorists in on what is important. And from that, we'll be able to develop that theory. So Enrico Fermi mentioned this to his colleague, Bernd Matthias, and Bernd Matthias took up the call. He more or less stopped working on ferroelectric materials and spent the next 35 years of his career discovering several hundred new superconductors. So this periodic table of the elements right here, for example, shows you that superconductivity is maybe not as rare of a phenomenon as you might think, because every element that's labeled in blue is superconducting when you cool it down to low temperature. Every element that has a little blue box can be convinced to become a superconductor if you both cool it to low temperature and apply pressure. So it's actually pretty prevalent out there. And then of course, there are many ways you can develop superconductors that aren't elements, binary compounds, ternary compounds, so on and so forth. And this idea worked because, after about 10 years of looking at that, Bardeen, Cooper, and Schrieffer developed their theory of superconductivity, published in 1957, which was able to explain finally the superconductivity type observations that had been made up to that point during the first 50 years of superconductivity research, and it was recognized with the 1972 Nobel Prize. Now, I wanted to mention a couple things before we go on. So Matthias really developed a procedure for making discoveries in materials, and it was more or less this. It was pretty simple. You need to develop rules of thumb. Okay, you can't throw darts at the periodic table. Develop rules of thumb for where you're going to look for new superconductors. And then once you've developed those rules of thumb, make as many materials as you can, and then test as many materials as you can. So it was sort of almost a factory type process. And, if I were to discover in the lab a new superconductor right now, I would publish it as a single paper and at a high level physics journal. In his day, he was sometimes publishing papers where it would more or less the gist was the following 100 new superconductors have been discovered, and then today that would be 100 different papers, but that's kind of the speed with which they were discovering these things. It's also interesting when we look at the history of the development of looking at superconductivity that a lot of the discoveries were completely by accident. So again, let's back to 1911, the original discovery of superconductivity by Heike Kamerlingh-Onnes. He was not looking for a new quantum state. Nothing like that was predicted. He was trying to determine, there was an open question at that time because we know the resistance decreases as a function of decreasing temperature. The question was, would that extrapolate to zero resistance at zero temperature? But not for any quantum reasons. They were just wondering if that were the case. And so Heike Kamerlingh-Onnes discovered superconductivity in 1911, completely by accident in mercury. So you can see on this chart, these sort of represent superconductors with the highest temperatures. So it's temperature on the y-axis and the year in which they were discovered. So after Onnes discovered superconductivity by accident, you can see that, some progress was made, in the next 30 years or so. We were up to about 15 Kelvin as people started working through elements and binary compounds. And basically everything on this curve here is a superconductor that would be very well understood using the BCS theory that I mentioned. The 1957 theory explains these superconductors quite well. And Matthias was mainly working on these type of superconductors. And his empirical rules of thumb included things like, you don't look at oxides, only look at intermetallic compounds. You don't look at materials that have a magnetic order to them, especially ferromagnetic. In general, you just shouldn't look at materials that have magnetic moments at all. And so these rules of thumb guided a lot of the research and also led to a lot of surprises, because in 1979, we can see these green data points down here. Superconductivity was discovered in cerium copper-2 silicon-2. This is they called it a spin fluctuation compound at the time. Now we know it as a heavy fermion, and it's a material that contains a lot of magnetic moments. And Matthias's rules said, don't look at these. So, when they were studying these, they were not looking for superconductors. This was for a completely different purpose. And yet they discovered by accident superconductivity in cerium copper-2 silicon-2. And in fact, you can see the next one on that list is uranium beryllium-13. And it's given a year of discovery like 1984 or so. That had actually been discovered to be superconducting in 1975, even before cerium copper-2 silicon-2. And the authors of that study refused to believe their own eyes. They still published the data, but they said, no, this can't really be superconductivity. There's impurities, uranium filaments running through the sample, which are superconducting and fooling us. Nope, they had actually discovered bulk superconductivity and they didn't believe it. Now, what's important here is this green line. All of these superconductors are what we call unconventional superconductors. So I said the BCS theory was a great comprehensive theory for superconductivity. It does not in any way explain what's going on with these. So once again, we have this situation where, you have this lack of understanding, and that's being alleviated, hopefully, by looking at and finding more materials and gathering more information. And that happened again in 1986. You can see these blue data points here. Scientists working on lanthanum-2 copper oxygen 4. They're working with oxides. Again, Matthias's rules say, yeah, no superconductivity in those. So they were looking at it for different reasons, but happened upon a 30 Kelvin superconductor. And one of the things you notice here is the title of their paper is written right here. The title of their paper is Possible High Temperature Superconductor in the System. Again, they were hedging because people would not have expected it there. And, even though their data showed it to be true, they're still kind of throwing that shade of doubt in there. And what you'll notice is that, very quickly thereafter, people looked at related copper oxide compounds and quickly increased the temperature at which superconductors can be found to almost halfway to room temperature. So these are all kind of related, what we call copper oxide materials. And then it happened yet again, it's not on this graph, but in 2006, scientists in Japan were looking for transparent semiconductors to use in computer screens and other displays. And one of the rules is, you don't look for superconductors among things that are ferromagnetic. And so you would not expect to find superconductors that contain iron. And yet they found an entire new class of superconductors based on iron nictide or iron chalcogenide units. So again, completely by accident, discovered a whole new class of superconductors. And so these green ones, the blue ones, and those iron nictide and iron chalcogenide based ones are all unconventional superconductors. They're not explained by the BCS theory. And so we're looking for, after 40 years, that comprehensive theory that's able to describe these. And again, it's not for lack of trying. And it's not that there aren't theories out there. There are 20 or 30 of them. It's just there's not consensus around who's right. And so until we know the best approach forward, the way that discoveries seem to be made is by continuing to make more materials and measure their properties. So the materials-driven approach usually kind of comes in two flavors. So either we're prospecting for new materials with a given property, or we're attempting to understand a particular type of property like superconductivity in a known material. So when we're prospecting for new materials, we're using kind of an Edisonian approach, but again, it's not throwing darts at the periodic table. We're usually picking a particular crystal structure and focusing on samples with elements, particular elements or building blocks. Like the copper oxide-based superconductors I mentioned are a good example. The first one, the crystal structure has these copper oxide planes in it, And people within a few years were able to look at related compounds with crystal structures that also had kind of these copper oxide type layers in them and discover superconductivity at higher and higher TCs. So, you know, you kind of go in this iterative approach, and I'll have another example on the next slide of that. Or we might look at a particular type of behavior and try to understand it by picking a known material that exhibits it and poking it with a stick. And the sticks at our disposal are chemical substitution, so replacing one element with another, applying pressure, applying magnetic field, maybe changing the dimensionality. So if you have a bulk material, you make a thin film or a nanorod, maybe you change the length scale, do some nano engineering. And you do these things to observe the response of the system to changing conditions in the hopes of better understanding its nature. So a good example of kind of this approach for prospecting for new materials is found here. So in around 1998, a group in England was looking at cerium indium-3, which cerium has magnetic moments. So when you cool it down to low temperature, below about 10 Kelvin, it becomes antiferromagnetic. So that's a particular type of ordered magnetic structure. And then what they found is if they applied pressure, that weakened the interactions that give rise to that magnetic order, so that it occurs at lower and lower temperature as you increase the pressure. And then eventually, at enough pressure, they had completely suppressed the antiferromagnetic state and out-popped a dome of superconductivity. So superconductivity below 0.2 Kelvin. Now, of course, this is not much to write home about. 0.2 Kelvin is very low, and it's under applied pressure. So we're not going to be able to do much with this as is. But in looking at that, you know, cerium indium-3, there are other crystal structures out there that have kind of that cerium indium-3 component or building block built into them. And one good example is cerium cobalt indium-5, which has some cerium indium-3 layers and a cobalt indium-2 kind of blocking layer in between them. And sometimes these can exert what we call a chemical pressure. So if cerium indium-3 becomes superconducting under applied pressure, you know, maybe chemical pressure here would induce superconductivity at ambient pressure. And that's what they found. They found superconductivity at 2.3 Kelvin without needing to squeeze the material. So, you know, it just took a couple of years, but they were able to go from 0.2 Kelvin to a material with 2.3 Kelvin. And then it only took a year after that for people to kind of tinker with cerium cobalt indium-5, and they replaced the cerium with plutonium and the indium with gallium. Not everybody can work with plutonium, but there are a few groups out there who could. And at ambient pressure, they found almost a 20 Kelvin superconductor. So in 2 steps, we went from 0.2 to almost 20 Kelvin, a 100-fold increase in TC. And so this is kind of, you know, what we mean by this materials-driven approach and kind of what this looks like when it's really successful. Okay, so I don't have a lot of time, but I wanted to just mention a few things about some student research at Central that, you know, is making use of some of these methods and looking at correlated electron phenomena. So I've had about 13 students working with me the past 4 or so years at various times, and, you know, they've done things like designing, constructing, programming all the temperature control, calibrating thermometry for cryostats, basically building instrumentation to perform measurements of things like electrical resistance and magnetic susceptibility as a function of temperature down to 4 Kelvin. And one of the students is working with me right now, almost has one of these finished, and it's working really well. So it's very exciting, and that's Martin Mattis. I had a student working on lanthanum-2 nickel oxygen 4, replacing some lanthanum with strontium. And the reason he was interested in that is lanthanum-2 nickel oxygen 4 has a very similar crystal structure to lanthanum-2 copper oxygen 4, which was one of those high temperature superconductors. And people noticed really early on back in the 80s that a lot of these nickelate type conductors looked very similar to cuprates, the copper oxides, but none of them exhibited superconductivity. So people have been, you know, kind of wondering why, and looking for superconductors among nickel oxide compounds. So that's kind of what intrigued the student. And the student has graduated and gone on to graduate school now. And it's kind of funny that about a year after they left, the very first nickel oxide-based superconductor was discovered just a couple of years ago. So now one is known, but that was the origin of that project. Another student was looking at kind of what happens around a phase transition in the element nickel. So that's something called critical behavior. Another student was looking at the unconventional superconducting state in barium bismuth oxide, and looking at what happens when you systematically put in lanthanum and cerium into this compound. The reason is lanthanum does not have a magnetic moment and cerium does if it's 3+. And so basically you can look at pair breaking by non-magnetic versus magnetic impurities. And this is one of those situations where you can learn something about the superconducting state by seeing how quickly you kill it by doing this. So that was kind of the goal of that project. Had students doing some prospecting for materials with enhanced magnetocaloric, and I'm interested in starting with mechanocaloric effects. So those would be apply a magnetic field and the sample changes temperature, or mechanocaloric would be apply pressure and the sample changes temperature. And these could have applications in new cooling devices, you know, making a magnetic refrigerator, for example, for your home or for your air conditioning unit. And then the one I'll go into just a little bit more is investigating low dimensional magnetic order in calcium-3, cobalt-2, oxygen-6 with zinc substitution. So I'll kind of zip through it because we're running a little low on time. But basically, here's the idea. Calcium-3, cobalt-2, oxygen-6 has a crystal structure that looks like this. We call it a low-dimensional magnetic system because the cobalt ions form themselves in these chains that run up the C-axis of the crystal structure. And it's cobalt 3+, but we have sort of this variation. So we've got octahedral coordination followed by trigonal prismatic coordination. So sort of different local environments that alternate. And if you look at this from the top, these chains form these nice equilateral triangles. And so what happens is on the octahedral site, these cobalt 3+ ions are in a low spin state, so there's no magnetic moment there. But in the trigonal prismatic site, it's a high spin configuration, so there is a magnetic moment here. And so magnetic moments can have exchange interactions with one another, and along a chain, they tend to be ferromagnetic, which means the little magnets want to line up together. And if you look at the interaction between the chains, that's an antiferromagnetic interaction, which means they want to anti-align with one another, although this is a lot weaker of an interaction between the chains than within a chain. And so we have this interesting interplay between magnetic frustration, and that's associated with this kind of triangular subunit of the lattice, and low dimensionality, and it produces a really complex phase diagram, a lot of different magnetic structures that exist. So, you know, basically, if you take this material and cool it down to low temperature at about 24 Kelvin, and if you're not applying magnetic field, you get something called a spin density wave, which is a type of magnetic order. But it's an unstable order because as you further cool below 10 Kelvin, it actually turns into, you keep a little bit of that spin density wave, but it sort of degrades into a commensurate antiferromagnetic order and some short range magnetic order. So you got 3 different types of magnetic structures that are coexisting. That's a really complicated, highly degenerate situation. And actually, it gets even more complicated when you apply a magnetic field. So right here, we've got magnetization as a function of magnetic field. If you apply a magnetic field, you get these interesting jumps and plateaus. Each one of these represents a new magnetic structure. So there are all kinds of magnetic structures that can be accessed depending on the temperature and field conditions of the sample. And you can see in this phase diagram that there are a lot of them right here. What we wanted to do was look at how replacing some cobalt with zinc would affect this. And so basically, you know, if we imagine that, you know, we've got 2 magnetic moments nearby one another, they have a ferromagnetic exchange interaction, means they want to line up with one another. The idealized spin chains for the parent compound look something like this. So we've got, you know, this kind of a magnetic exchange interaction, and we've got another one down here and this one here, and then a slightly, by an order of magnitude, weaker one between these guys right here. But if we replace it with something like zinc, which has no magnetic moment, we actually dilute the spin chain. Okay, so there's no magnetic moment here when I put a zinc there. And now I break up the magnetic order or the magnetic exchange pathways, and I have more of them. So I take what's already a complicated situation, and it seems like I make it even more complicated. We wanted to see what would happen in that situation. And the way we did it was by measuring heat capacity. This is a figure from the paper that we published, and I'm not going to go into all the details here, but you know, basically heat capacity versus temperature allows us to look at things like where are phase transitions happening and what is entropy doing. So this big lambda-like feature in the heat capacity is associated with the phase transition to the long-range ordered spin density wave in the parent compound. And these data are taken at different applied fields, so 0, 0.5, 1 Tesla, 1.5 Tesla, so on and so forth. And so you can see that by applying field that we're, sort of changing the character of this a little bit, and that's sort of a redistribution of how entropy is situated with the material. We could go into more detail, but we don't have time. And over here, we've got a little bit of zinc put in, and you can see that zinc has suppressed that order a little bit. So where that happens is a slightly lower temperature. It's also broadened the feature, and that's just a impact of sort of chemical and magnetic disorder. So those are all pretty typical things. What's interesting though is if we look at low temperature, if we look at heat capacity divided by temperature. Now, heat capacity divided by temperature, if you integrate that with respect to temperature, you get entropy. So basically the area under the curve of C over T versus T represents the entropy. And what you'll notice is in the parent compound, I've got this upturn that occurs in C over T. And that's telling me about a buildup of entropy at low temperature, which of course makes sense, right? Because I mentioned that we had one ordered state and then we cool the low temperature and it sort of degrades into 3 coexisting ordered states. There would be a lot of entropy associated with such a highly degenerate situation. So that's kind of what we're looking at here. But we can contrast that with the sample where we put zinc in, where that upturn isn't there. What happened is, we seem to have stabilized one of those magnetic orders so that we don't have the highly disordered situation that we have over here. What you can see also, if we take the entropy, so this is the change in entropy. Basically what we've done is we've taken our entropy at different temperatures and fields and subtracted off the zero field entropy curves. Again, for the parent compound, you get this buildup of entropy at low temperature associated with that more complicated entropy. But in the zinc doped sample, it's not there. So, at this point, we're forced to conclude that zinc substitution, which sort of counterintuitively seemed to make a much more complicated landscape of different magnetic exchange interaction pathways, actually stabilized one of those magnetic orders and led to less disorder. So that's kind of an interesting result. It's one that in order to determine which of those magnetic orders we stabilize, we would have to use more sophisticated techniques like neutron diffraction, for example, to really characterize. But this right here tells us something really interesting happened to the magnetic ground state of that compound by putting in zinc. And it's not without precedence. If you apply pressure to calcium-3, cobalt-2, oxygen-6, you stabilize one of those magnetically ordered states, and the other ones aren't there. And there's at least one example in the literature of replacing calcium with some rare earth elements where you stabilized a different magnetic structure, but again, reduced the disorder. So this seems to, maybe fit in with that paradigm. We also, the student was, a student who was working on this is working on a manuscript right now. We're looking at more globally, what replacing cobalt with some other elements might do. Basically this is the change in the temperature at which we have magnetic order versus the amount of that element we put on there. And you can see that, from the literature, basically our contribution was zinc. All these other ones are from the literature. But there's a wide variation. Some things actually strengthen the magnetic order a little bit. Most things suppress it, but at varying rates. Iron suppressing it very fast, manganese much less so. In order to try and come up with sort of a broad picture on why that might be the case, we looked at a lot of things like how big the ions were, ionic radii. And, we figured out that, smaller ions were those that tended to occupy the trigonal prismatic site. The larger ones tended to go on the octahedral site. But that didn't really necessarily explain all of the observations here. But one thing that was kind of interesting is these guys up here all go in as 4+ ions. These ones here, 2+, and these ones 3+. So it really, how rapidly or how rapidly we kill off superconductivity really seems to depend mostly on the oxidation state of the ion we're replacing cobalt with. And part of that could be, in order to satisfy charge balance, some of the cobalt, may have to change its oxidation state as well. So it's cobalt 3+ you're replacing it with, so you put a 4+ ion in there, some of the cobalt 3+ turn into cobalt 2+. And for anything with a 2+ ion, like the zinc and copper, some of the cobalt 3+ on an octahedral site have to become cobalt 4+. So we're also doing something to the cobalt in addition to replacing some of the cobalt. But interestingly, in the case of replacing it with trivalent oxidation state elements or ions, there's no change to the cobalt oxidation state, but that's the one that actually had the biggest impact on killing off the magnetic order. So that's something we're kind of looking into, and that's another student project that's ongoing. So I didn't want to go into too much detail there. I just wanted to give you a kind of a sense for some of the projects. So let me go ahead and just offer a few concluding remarks. So technological advances ideally could be made by discovering new or enhanced correlated electron phenomena. That's been the case with a lot of the advances we've made to date, that new materials have led to those, and I expect that to continue. But until we develop computational tools or models that are really capable of predicting which materials are going to exhibit these properties, most of these advances will probably continue to be made by experimental discoveries. And the materials-driven approach of just making a lot of materials, measuring a lot of materials, offers an appealing blend of scientific interest, lots of surprises, as well as the potential to assist in developing future technologies. And finally, one of the things that I'm most proud of is the central students who have been working on the projects in my lab with me, have been able to develop some skills that have propelled many of them onto graduate programs in physics and material science or industry. And of course, I really enjoy correlated electron physics research in general, but here at Central, that's really what I view my primary role as, is to help educate that next generation of material scientists and help them meet their future career goals and education goals. So I'll go ahead and end it right there, and would happily entertain any questions.